In this lecture, which will be slightly longer than our other lectures, I'll uh, I'll cover this basic properties of these measures of information related to their shapes. How do they look as functions of the underlying distributions? For instance, are they non-negative? Are they bounded? Are they convex concave? I'll define what convex concave means. So are they convex concave, and so on and so forth. All right. Before I start, I wanted to present a very simple, a very basic inequality, perhaps not so simple, which is quite useful. Okay. And this inequality is called the log sum inequality. Okay. The log sum inequality. So what is the log sum inequality? So let me state that the log sum inequality says that if you have non-negative numbers ai and bi, so these ai and bi's are non-negative numbers. Let's say there are so I is between 1 and n. So let's say there are n non-negative numbers. Then log sum inequality says that summation over I equal to 1 to n, ai log ai by bi is greater than equal to summation over I equal to 1 to n ai log summation over I equal to 1 to n ai by summation I equal to 1 to n bi. So essentially you can take the sum inside and that will only reduce the quantity. Summation I ai log ai by bi is greater than summation over I ai log summation over I ai by summation over I bi. So we'll prove this inequality now. The proof relies on a simple elementary fact that I'll note down here. So this is about log x. The fact that you want to use is that log x, actually sorry, this is about the natural logarithm, ln x is greater than equal to, it's less than equal to x minus 1. Okay, this is the fact you would like to use. How do we show this? Well, this is something that you can plot and show. I don't know what it means to plot and show, but at least you can convince yourself by drawing these graphs. So this is what log x looks like. This is for x greater than equal to 0, by the way, this inequality. And this is what x minus 1 looks like. Okay, it stays above this. So this is x minus 1. How do you show this? Well, you can. There are various ways of showing it. First is that you can start from x equal to 1 and try to show how they behave at x equal to 1 and extend it. Alright, so this is the log sum inequality above here, and we'll use this fact to prove it. How do we prove log sum inequality? Okay, proof. So one thing we notice is that if we take this thing on the right hand side to the left side and subtract, what we are required to show, so this is to show summation over I ai log ai by summation over I equal to 1 ai, this is some constant sum, by bi by summation I equal to 1 to n bi is greater than equal to 0. That's what we have to show. In fact, you can also divide by this same summation over ai because it's all terms are non-negative, so you can divide by it. So you have to show this is greater than equal to 0. If you look at these new terms now, I'll give them a name. I'll call them ai primes. Okay, I'll also give these guys a name. These are bi primes. If you look at this ai primes and bi primes, they sum to 1. So they are non-negative and they sum to 1. So they are basically, these guys look like PMN. So what we are saying here is that it suffices to show this inequalities for ai and bi's with sum to 1. And that's what we will do. We'll now assume without loss of generality. This is a phrase used quite often in mathematics. Without loss of generality, which means that if we show it under this assumption, it implies a general result. So assume without loss of generality that AI prime I equal to 1 to n equals to bi prime, the sums, n equals to 1. So both are normalized to 1. So these are like PMFs. Okay, so let's just show for this case. So we have to show summation I equal to 1 to n ai log ai, sorry, this is, I don't need a prime here, ai by bi is greater than equal to 0. I'm assuming this sum to 1. This is what you have to show. So let's do the following. Let's switch this b and a. Okay, just this. So it's the same as showing that bi by ai, this is equal to minus of the term we have, is less than equal to 0. That's what we will show. All right, how do we show this? So remember our basic inequality from here, this one. So using this inequality, log bi by ai is less than equal to bi by ai minus 1. So we'll substitute it here. So this implies summation I equal to 1 to n ai log bi by ai is less than equal to summation I equal to 1 to n ai bi by ai minus 1. So bi minus ai by ai, and this is equal to summation over I bi minus summation over I ai, but both summations are 1, so this is 0, and that's the proof. Okay, that's what you wanted to show. Right. So this is the inequality. We let me clear up. So this is the inequality we have shown, that summation over I ai log ai by bi is greater than equal to summation over I ai log summation ai by summation bi, log sum inequality. If you take the sum inside, then it decreases. The way to remember this inequality is that a here is in the a here is the one in the numerator. Okay, so now that we have shown log sum inequality, we'll find many applications of this. Oh, sorry, just a small thing here. This inequality I have to do it with natural log, and but this log can be written as ln by log of e. So you have this sorry, what am I saying? Log to the base 2 can be written as ln by this, and so yeah, you have 1 by ln 2 here, but doesn't change much. It's still 0. Okay. All right. So when does equality hold here? That's something that whenever you have an inequality, you try to figure out when does equality hold here, or if equality holds here. Okay, so does equality hold for this inequality? Well, if you see carefully, the only place where we have used inequality is this one. We have said log x is less than equal to x minus 1. When does equality hold for that inequality? Equality holds if and only if x equals to 1. So equality will hold if and only if this x bi by ai is equal to 1. Therefore, equality holds with equality if and only if ai by, since we have normalized these ai's for this, equals to bi by this normalization. Okay, this is the only condition. The equality holds if and only if this one holds. All right, so we are done with log sum inequality. So equality holds if and only if the normalized ones are equal. If ai actually sum to 1 and bi sum to 1, then equality holds if and only if ai equals to bi. Next, I want to define convex and concave functions. These are some important shapes that we'll be encountering throughout this course. Okay. So convex and concave functions. Simply speaking, a convex function looks like a cup, like this. A concave function looks like a cap. Okay, so convex is cup, concave is a cap. Okay, these are convex and concave functions. More formally, a function is convex such if the following property holds. Take any 2 points and look at the line joining those 2 points. This line must lie above the graph. This is a convex function. Similarly, a function is concave if this line lies below the graph. Okay. So what is the formal way of writing it? A function f is convex, let's say over Rn. So let's just think of functions which are taking values from Rn. If for any theta in 0, 1, so take this theta between 0 and 1, how do you parameterize a line? You take 2 points and move the point by a fraction theta. So this is the parameterization of a line. So if for any theta times fx, so there are 2 points x and y, plus 1 minus theta times fy. As you move this theta, this point moves from this corner to this corner. So you can just think of this point here as x, this point here as y. Okay, so you move from fx to fy. This guy is, as I said, exceeds. So the average of f exceeds the f of average. Theta x 1 minus theta y. Okay, that's the chord. So when you move this point here, this is the average in f, and look at the corresponding point here. Don't take below. Okay, this is a definition of a convex function. A function is concave if minus of that function is convex. Okay. So more formally, it's f is concave if, such similarly for all theta in 0, 1, this is for all, notation for all, theta fx plus 1 minus theta fy is less than equal to f of theta x plus 1 minus theta y. Okay, that's a convex, it's a concave function. Okay. So now I want to point out a very basic and important property of this convex concave functions. So we saw that by definition, this convex concave functions, for this convex and concave functions, you can fix any one. Let's think of convex functions. The concave is the minus of that function, so the inequality flips. So for these functions, the value at the, let's say for convex functions, the average of value exceeds the value at the average of points. So you can repeat this property. From 2 you can go to any finite number of points. First you can go to 3 points by applying it to just repeating it 2 times, and then 4 and so on and so forth. So you can go to finite number of points. But in fact, the more general version of this bound holds, and that's called Jenkins inequality. So that's some very important tool to remember. I'll note it down here. Jenkins or Jensens, I guess. I don't know. Jenkins inequality. What does it say? It says that if f from Rn to R, so it is a convex function, then take any distribution on the input. Okay, so x, let's say, is a random variable, taking values in Rn, then expected value of f of x, this is this part, right? Average of values, theta with probability theta takes value x, with probability of minus theta takes value y. This guy is greater than equal to f of expected value. Okay, average of values is more than value at average. That's Jensen's inequality. So if we look at some examples of convex functions, so here are some examples of convex functions. X square is a convex function. In fact, all linear functions are both convex and concave. All polynomials with power greater than, all monomials like this, x2, x3, x4 are all convex. And a good example of concave function is square root x maybe. But more importantly for this course, one very important concave function is log x. Okay? Log x is a concave function. And therefore we can apply Jensen's inequality to this. This is for convex function. Similar, there's a corresponding inequality for concave function. Just the direction switches. So for concave function, what happens is expected value of fx is less than equal to f of expected value at x. Expected value of x. Okay. So this is for concave functions. The direction switches. Okay, so let's see what happens for this example, x square. For x square, Jensen's inequality implies, since it's concave, Jensen's inequality gives you that expected value of x square is greater than equal to expected value of x whole square. It's a very well-known inequality. Basically, this is saying variance is non-negative. Remember, a difference of these two quantities is the variance of the random variable. Similarly, log x, for log x, which is a concave function, the expected value of log of any random variable x is less than log of expected value. Okay, the specific random variable that we can choose as an example is this random variable, which is just qx by px, the ratio of two PMFs, and the expectation we take with respect to p itself. Okay, and so you can take this expectation inside. So what does it look like? Expected value of qx by px, that's summation over x, px qx by px. So px cancels and it's summation over x qx, which is log of 1, which is 0. So this basically, this inequality here is the same as, so what is this saying? It's saying so this is saying summation over x px log px by qx is greater than equal to 0. This we didn't remark on it then, but this is basically saying that divergence is non-negative, which is also same as the log sum inequality. So this is an alternative proof of log sum inequality. And Jensen's inequality indeed is much more powerful than just log sum inequality. Okay, so this is something about convex and concave functions. We have this Jensen's inequality holding for these functions. All right. So by now you would have seen that so we will not prove Jensen's inequality, but there's some important property. So we have all the components to now claim that all our functions, the information theoretic functions that we have seen, are non-negative. So I'll write this lemma and quickly walk you over the proof. Okay. So the following hold for, the following hold for discrete random variables, discrete distributions and random variables. Let me just say it for discrete distributions. In fact, it holds for any, but I'm showing it only for discrete and random variables, some short form. So there are three properties I'll claim. So first one is dpq is non-negative, okay, with equality if and only if p equals to q. Okay. So how do we show this first one? This is exactly as we notice here, Jensen's inequality or log sum inequality. We gave a specific proof. When was equality in log sum inequality? When the elements are equal, ai is equal to bi, and so this is that condition for equality. All right. Mutual information, remember, is the divergence between dpxy and pxpy. Therefore, this is also non-negative. And with equality, if and only if pxy equals to qxy. Sorry, pxy equals to pxpy. So what is this condition? This pxy equals to pxpy, which is the condition for equality of mutual information. You can stare at it and try to think about it. This is basically saying if and only if x and y are independent. Only for independent x and y, pxy, the product, the joint distribution is equal to product of marginals. So mutual information is non-negative, but it's zero if and only if x and y are independent. Third property, it's about entropy. The third one says that entropy h of x is greater than or equal to 0 with equality. So when is entropy 0? So we've already seen actually that when is entropy 0, but I'll revise this property. If and only if, this is a short form for if and only if and only if x is a constant. Yeah, this is easy to see because h of x is simply summation over x px log 1 by px. All terms are non-negative in that sum. But when is that sum equal to 0? When all terms are 0. These terms can be 0 either if px is 0 or if px is 1. So convention we are following is 0 log 0. This is not, it's some convention you have to follow. It's not easy to define as 0. That's a convention. So 0 log 0 is 0. Log is not defined at 0. We can define it 0 log 0 is not defined at 0, but we can define it as 0 because that's the continuous extension. Okay, so it's constant if an it's 0, hx is 0 if and only if each term is 0 or 1, each px is 0 or 1, which only happens when x is constant. There's another way of seeing it. Note that this h of x is equal to the mutual information between x and itself. And when is a random variable independent of itself? When it is constant. So you can get this from property 2 itself. Okay, so here are these three properties about non. So all these measures are non-negative and they are 0 under different conditions, right? So this is the an important lemma. Okay. It has told us that all our measures of information are actually non-negative. Let me highlight it. Right. So it's something that you should remember throughout the course, and we'll use it quite often. Okay. So this is the first shape property we have seen. We have now shown that all our random variables, all our measures are actually non-negative. Okay. So we saw this convex concave functions. Now we have shown that. This is the third part. Sorry. Okay. I'll name this lemma the non-negative measures of information. So all these measures are non-negative. If these guys are non-negative, their conditional variants are also non-negative. Okay, so fourth part. So this fourth part now is about boundedness, okay, of these functions. So these functions are non-negative. Next thing I am claiming is that they are also bounded. So I'll show different properties for this boundedness. So first property is very commonly studied. It's a uniform distribution maximizes entropy. What do I mean? What I mean is that if you look at any random variable, so for a PMFP on X, okay, H of P, the entropy of P, is less than equal to, make some space, this H of P is less than equal to log of cardinality of X. And this guy, if you see, is entropy of the uniform distribution on X. And when does equality hold? With equality if and only if P equals to P uniform. So how do we show this? Here is a simple proof. The proof just notices that that the divergence between P and P uniform is actually log of cardinality of X minus H of P. You can check that. And we already saw that in the previous lemma, this one, we saw that divergence is non-negative and equality holds if and only if P equal to Q. And this is simply a consequence of that property. So this guy is non-negative with equality if and only if P equals to P uniform. Okay, so uniform maximizes entropy. H of P is always less than equal to log of cardinality of X. This is true for, let's say, X with finite cardinality. This is a very important property we should remember. Throughout this course, we should remember this property. Okay. Now, so we know which distribution maximizes entropy among the ones with finite cardinality. But we can define distributions, discrete PMFs, over an alphabet of countable, over a countably infinite alphabet like natural numbers. What happens in the case of such distributions? Well, there is another result which is the counterpart of this result for that such a random variable. So I'll put it down. And this is geometric distribution maximizes entropy. Okay, so uniform maximizes entropy over this finite alphabet. Geometric distribution maximizes entropy over such an alphabet. So consider a PMF P or a distribution P on n, the natural numbers. And suppose the expected value of this random variable, the distribution P, is equal to alpha. Okay. Then this is the second result. H of P is less than equal to log alpha minus 1 plus alpha log alpha by alpha minus 1. Okay. So so we can see it in another way. This is alpha log alpha minus alpha minus 1 log alpha minus 1. And what we will see soon is that this right side here, this guy here, is this one here is entropy of a geometric distribution with mean alpha. So among all distributions with given mean, the geometric distribution maximizes the entropy. Just like among all distributions on an alphabet of given size x, uniform distribution maximizes the entropy. Similarly, among all distributions with a given mean, geometric distribution maximizes the entropy. So how do we show this? Yeah, so it's a very similar proof as this one. So proof. Let's look at the divergence between the distribution P, another distribution Q, which is the geometric distribution. So this guy here, this is the geometric distribution. Okay, with mean alpha, let's say. So how do we define geometric distribution with mean alpha? It takes Q of I equals to 1 minus P into P to the power I, and this is for all I in natural numbers, And this P is, because you want the mean to be alpha, this P is alpha minus 1 by alpha. That's a geometric distribution. So we can say, we can use any distribution here. And of course, this quantity is non-negative with equality if and only if P equal to Q. But what is this quantity? This quantity is exactly equal to summation I equal to 1 to infinity Pi, use a small q here, log Pi by Qi. Maybe P is not a good notation. I'll call it something else. Maybe theta. Let's call it theta. I'm using P here. Okay. All right. So this is this quantity. This Pi log Pi, this is entropy. So minus entropy comes out. What about log of 1 by Qi? Log of 1 by Qi. So we'll substitute the formula for Qi. So this is 1 minus theta, theta to the power I. So we can continue. This is 1 by that. So minus so this is minus log 1 minus theta. This is this term. And theta to the power I. So that's minus log theta to the power I. That I comes out. And expected value of that I is what gets remains here. Okay, so that's just expected value under P of this random variable x minus HP. So this we have already fixed as alpha log. So this is alpha minus 1 by alpha. Then there's a minus sign. Yeah, it's a minus sign. And minus log, what is 1 minus theta here? It's 1 minus 1 by alpha. So 1 minus theta is 1 by alpha. Right. I make a mistake here. Oh, sorry. Yeah, let me go over this quickly again. Okay, so sorry about this. This is I minus 1. Okay. Do this calculation one more time. So we are looking at summation I equals to 1 to infinity. This should be I minus 1. That was the mistake. Pi log of 1 by 1 minus theta. Let's keep it here. Plus summation I equal to 1 to infinity Pi I minus 1 log of 1 by theta. And this minus HP remains here. Okay, so what is this quantity? Pi log 1 minus theta. This is just a constant. So so theta is so this is theta. Theta is 1 minus 1 by alpha. So 1 minus theta is 1 by alpha, and 1 by 1 by alpha is alpha. So this term is just log alpha. And what about this guy here? So 1 by theta is alpha by alpha minus 1. So log alpha by alpha minus 1. And expected value of I minus 1. So that's alpha minus 1. Okay. So if you expand this, you can see this looks like alpha log alpha, alpha log alpha. And this minus cancels with this one, minus alpha minus 1 log alpha minus 1. Okay, this is exactly the entropy of the geometric distribution. So in conclusion, this guy is non-negative with equality if and only if P equals to Q, the geometric distribution. Very cute. Okay, so these two proofs are very similar, and this is something to remember. Uniform maximizes entropy over distributions with bounded support. and geometric maximizes entropy over distributions with given expected value. All right. So now we have seen that entropy is bounded, and therefore mutual information over finite alphabet, or over finite alphabet at least, will also be bounded. They're all non-negative, they're bounded. The last part that you want to discuss about shapes of this random variable is something to do with their convexity or concavity property. So we already know what convex and concave functions are. So convexity, concavity. Okay. So are these functions concave or convex? That's what you want to figure out. So the main result in this category is about KL divergence. dpq is a convex function. Convex function of the pair. So I'm thinking of it as the function of the pair itself, of the pair. So if you think of dpq as a function of the pair of distributions, claim is that it's a convex function of the pair. So how do we show this? Well, we take two pairs, p1q1 and p2q2, and we take some theta in 0, 1, and then we look at the let p theta be the average of p1 over theta, of p over theta, and let q theta be average of q over theta, weighted average of q weighted by theta. So d p theta q theta equals to summation over x p theta x log of p theta x by q theta x. Let's expand this thing. This is equal to summation over x. Just look at the inner part here. This is theta p1x plus 1 minus theta p2x log theta p1x plus 1 minus theta p2x divided by theta q1x plus 1 minus theta q2x. Okay. Now if you look at this sum, this looks like think of this term as a1, think of this term as a2. So the a1 appears here also, and a2 appears here as well. They're all non-negative terms, and this is my b1 and this is my b2. So this is a1, a2, a1, a2, b1, b2 plus b1, b2. This is basically the setting for Jenkins log sum inequality. And what we can conclude from log sum inequality is that each of this is less than equal to, each sum n is less than equal to this. Therefore, the sum is also less than equal to a1 log a1 by b1 plus a2 log a2 by b2. So what is a1 log a1 by b1? a1 log a1 by b1, theta p1x by theta q1x. So theta gets cancelled, p1x by q1x. And similarly, 1 minus theta p2x log p2x by q2x. And therefore, this guy here is equal to theta p1 q1 plus 1 minus theta divergence p2 q2. Okay, so that's the proof that pq is actually convex function of the pair pq. This convexity in the pair itself is a very strong property. And so this convexity in the pair is very strong property, and we can so value at the average is more than the average of value, so it is indeed convex. and it's a strong property, and we can derive other properties out of it. For example, if dpq is convex in the pair, then so this is a corollary, so-called corollary. So what it follows from this observation, that if you fix any p, if you fix any q, let's say dpq is convex in p for any q, for any fixed q. You fix a q and vary p, it's a convex function. And similarly, dpq is convex in q for any fixed p. That follows. But in fact, more properties will follow, because we have already seen that all functions like entropy and mutual information can be expressed as divergences. So another corollary is that h of p is concave in p. So concave functions look like a cap, and they can be maximized. So this function is concave in p. How do you show that? Well, proof is very simple, given that we've already shown something stronger. So d p uniform, p with p from a uniform distribution, is log x minus hp. So if for a p uniform, if d is, this is convex in p, therefore hp is log x minus dp p uniform, and that's concave in p, because it's minus of, it's some constant minus, constant don't change the shape, constant minus this is concave. Okay, so entropy is a concave function of p. This is a very important property. Okay. And there's another interesting implication, but we have already seen that. We already saw that mutual information was non-negative. That's something that we claimed earlier. And what this also implies is that h of x is greater than or equal to h of x given y. So this property is often stated as conditioning reduces entropy. But this property can also be seen from the concavity of entropy. Okay, so this one implies this. How? Since entropy is a concave function, this conditional entropy is the expected value of h of x given y. And because h is concave, I can take the expectation inside and it will only increase the function. So this guy here is expected value of p of x given y. So you take the expectation inside, it's the expected probability p of x given y. What is this expected probability? This is nothing but p of x. So this guy here is h of x. So this is an alternative proof of the fact that conditioning reduces entropy. We already saw it from mutual information. Right? Now, finally, how about mutual information? Is it convex or concave? So this is interesting. Last property that you want to see. Okay, I'll make some more space. So entropy is concave, divergence is convex in the pair, and in fact divergence is convex in any one argument. How about mutual information? That's the last thing we want to figure out. So mutual information is both convex and concave. What do I mean? Actually, not so much. This is not a formal statement. It's just something I want to say. Okay. So here are the two results that I'll show. So I'll again call them this lemma. So the first lemma is that mutual information IPW is concave in P for every W. So if you fix the channel and change P, this mutual information function will be concave in P. How do we show that? So one way to see this is, this mutual information can be written as entropy of the output distribution Y, which is, this is Y, minus the expected value over P, entropy of W of X. Right? So this is, if you can't recognize this quantity, this is H of Y minus H of Y given X. Now, this function here, the entropy function, is a function of this linear function. So this is a function of W of P. What is W? W of P can be seen as a new distribution, which is the linear combination of X. So there are several distributions, one corresponding to each X. So think of this distribution over Y, one for each X, and you weigh them by, so these are all vectors, and you weigh them by Px. Okay, so this vector is obtained by some linear combination of Px. And this guy here is summation over X, Px, H of Y given, this is some notation I'm introducing, maybe I'll do a better job than this, P of Y given X equals to X. Okay, this is a better notation. Right, so this is this. So this guy is a linear function of P. And this guy here is a linear function of P, but it is an H outside. So this is a linear, this is a concave function of a linear function. So you can show first that linear functions are both convex and concave. Okay, so this function is actually, this entire thing is concave. And this is a concave function of a linear function, therefore this is also concave. And sum of two concave functions is concave. These are the three steps in which it follows that this is a concave, IPW is a concave function of P. Okay, so you can fill in the details. Okay, how about, so this is a rough proof. How about IPW for a fixed P? So this is convex in W for every fixed P. Okay, so for every P. So if you fix the input distribution and change the channel, then this is a convex function. By the way, one interesting consequence here is that you can sort of so you should somehow imagine that you can maximize concave functions. So you can maximize this guy over P. And is there a reason why we should operationally expect this measure of information to be convex in W? Well, here is one reason. Any channel can be thought of as convex combination of useless channels. Not useless channel, convex combination of perfect channels. What is a perfect channel? It takes X and just sends it without any noise. Okay, that's just, I'm saying something rough here. And this is the most informative channel. When you take the average of this channel, you get the original channel, and this channel must have lesser information than the perfect channel because perfect channels have full information, some heuristic. So this is sort of an expected property. This convexity of I in W is an expected property. Similarly, concavity of I in P for a fixed W is a useful property because now we can maximize over P. So how do we show this? So, so the proof, we again take these two channels W1 and W2 and look at this guy. And once again we use that log sum inequality, and we notice that this guy here is summation over X Px, and then something very long. Let me just make some space for myself. Summation over X Px summation over Y theta W1 of Y given X plus 1 minus theta W2 of y given x. I'm just expanding the formula for mutual information. You can do it yourself. Same thing, theta W1 of y given x plus 1 minus theta W2 of y given x divided by theta W1, the output distribution now. So please verify that this is indeed the correct formula for mutual information. Make some space. W2 of y. Okay, so now let's try to see. So this term here is my A1, A2. Same A1 shows up here, A2, and these are my B1 and B2. So I can apply log sum inequality. And by log sum inequality, this guy here is less than equal to summation over xpx, summation over y theta w1 y given x log of theta w1 y given x by theta this, so that theta cancels, y w1 of p y. So if you see this guy, we can recognize it as just theta times mutual information between p and w1, and similarly theta times 1 minus theta times mutual information between p and w2. Okay, so this is less than equal to this, and that's just convexity of p. Okay, so in summary, okay, this concludes this lecture. There are many properties we have seen. Let me quickly go over those properties. Yeah, it's a long lecture. So we have seen that all these measures of information, all these measures of information are non-negative. Then we saw that entropy is bounded by log x for uniform, by log x if the cardinality of x is finite, and by this entropy of a geometric distribution with a mean alpha if the mean of x is alpha. Then we saw that divergence is jointly convex in the pair PQ, which further implies that divergence is convex in any one of its argument, and which also implies that entropy is concave in P. And finally, we saw that mutual information is actually concave in the first argument, P, the input distribution for a given channel, and convex in W. Okay, that's all we saw. So we now basically understand the shape of this thing, these bounds. Let me conclude by just plotting something about H. So we saw that H of P is concave function of P. So if you look at the binary entropy function, which is the entropy for the binary random variable, okay, that's the formula for this guy. Now this function we have said is, so this is P is between 0 and 1. Let's look at it as a function of P. So we know it is concave. We know it is bounded by entropy of the uniform distribution, which is 1. And it is non-negative, so it stays here. And uniform distribution maximizes entropy, so that's half. So it reaches half, 1 at half, and it's a concave function. So this guy looks like this. Okay, so that's the shape of the entropy function. All right, so we have covered shape of all the measures of information, and in the next lecture, which is the final lecture for this week, I'll cover the data processing inequality. See you in the next lecture.